So we're using chemistry we've used before. We're getting a decarboxylation as a result of letting this double bond within the thiazolium ring act like our carbonyl in an aldol type reaction, one of our carbanion bond breaking reactions. Kind of sneaky, right? That was not slick, that was sneaky, right? We snuck in a C double bond N on them so that we could break that bond. Does that make sense?
What was that for?
This is the pyruvate decarboxylase, right? This is the coenzyme interacting with the substrate in pyruvate decarboxylase. Okay? So now we've decarboxylated that. We protonate it with something. And now, if we can drop this down, right? We know this was already stabilized as a carbanion, so it can act as a leaving group. We essentially get an elimination reaction. This leaves, this comes down, and you end up with your aldehyde product. And we're back to this form. Elizabeth's not nearly excited enough about this.
Isn't that too strong of a base to be a leaving group, though?
No, in this case it's not.
But it's strong enough to be. It's still strong enough to be a good nucleophile.
Yeah. Again, probably promoted. I would guess there's something here, some basic group here, pulling in on this hydrogen ion, that's making these electrons start to look for someplace else to go. Right. So if there's something else helping this, then you've got a better chance of that happening. Okay? I have to wake Melanie up. I have to start going faster.
No.
Okay? And then we've talked about the reduction. So here is alcohol dehydrogenase. So NADH. The hydride acts as nucleophile, opens this up. Right? Zinc is acting as a Lewis acid to pull on these electrons to make this spot a better electrophile so that we get the reduction. Then a hydrogen ion takes the place of the zinc, and you have ethanol. I had to show that just so I could show the mechanism of alcohol dehydrogenase once. Not that it's that cool. I just had to show it once. Okay? So that's the first one. Right? That was door number 3. So if we go back up here, let's say this one, right? Because this one is the citric acid cycle. That's going to be a whole chapter on its own. So let's ignore this one. So since we started with door number 3, let's go to door number 2 now. That is homolactic fermentation. So, lactic fermentation is really straightforward. You have lactate dehydrogenase, right, named in this direction. But if we have high NADH and high pyruvate, it will go this direction. As a matter of fact, since this is high energy, the equilibrium lies this way for these enzymes. So we've got NADH we made in glycolysis. We reduce the ketone to a specific stereochemistry, the L stereochemistry of the lactate. Right? We only get one stereoisomer here, directed by the enzyme. We have NAD. They can go back up to that glyceraldehyde 3-phosphate dehydrogenase reaction and go through glycolysis again. Right? So where do we get a lot of homolactic fermentation, lactic acid production? Jordan? Well, we've all experienced one of them.
Muscle.
Muscle, right? Walk to the top of the stairs, you feel it in your legs. That's the buildup. What's the difference between making lactate and making ethanol?
We can make lactate.
We can make lactate, we can't make ethanol. There's one thing. Give me another difference. Thinking about what we said the advantage of making ethanol was.
That can't.
Yeah, why can't it diffuse? Yeah, it's charged and we got a charged group and a polar group. It's too charged and polar to diffuse out. So this can't get out of cells unless the cells have a way of transporting it. Our muscle cells do, at least in limited ways, but it's not that efficient. So what you're feeling when you get to the top of the stairs, or when you're running 400 meters, or I don't know, pick something. When you feel the Jane Fonda burn when you're doing your aerobics, right? I know I'm dating myself. Is the buildup of lactic acid, because as product builds up, what happens to the efficiency of this reaction? It decreases. And so as lactate builds up, the ability to convert the NADH to the NAD decreases. It slows down, which means that starts to limit how quickly glycolysis can occur. And who's had physiology? Who are my physiology experts? Robbie's the only one volunteering as a physiology expert today. In physiology, you talk about muscle contraction, right? The specifics of muscle contraction. What's the role of ATP in muscle contraction? What is it?
The head thing.
The head thing. The head thing.
I know it's
eloquent.
myosin and actin, but I don't know what the
Yeah.
power stroke, is that what it's called?
Well,
Something
That's what
like-
we learned in physiology.
yeah.
Phosphorylate
It phosphorylates the myosin head, but what happens when ATP binds to that myosin head? Yeah, so that's the release phase, right? ATP is involved in the release. And so what happens if ATP becomes limiting? The release becomes slower. What do you feel as lactic acid builds up in your muscles? You start to get cramp, soreness, right? Muscle contraction slows. Why? Which part of muscle contraction is affected?
The release.
The release. That's why your muscles start feeling stiff. It's because those heads aren't releasing as quickly, so your muscle can't recover for the next power stroke. They're sort of stuck there. And if they get stuck there too long, then what happens? You cramp or you get a tear. Yeah, right? Because the muscle fibers are locked up, and if you can't get ATP to them in time to get them to release before mechanical action pulls that, then you can get actual tearing of the fibers. So, right, from what we feel, right, this makes sense. We feel that stiffness as the production of ATP slows when NAD can't be converted back to NADH. Or I'm sorry, when NADH can't be converted to NAD. And so glycolysis slows. Okay, so there's one place that we deal with lactic acid. What are other places? Who's my micro expert? Have you had micro? Who's had micro? None of you have had micro?
Not real. I have, but it's nursing micro, so I didn't really
Still,
learn it.
in nursing micro, you talk about stuff a little bit. And then you're saying you don't? It's kind of not? Darn. Right? But you talk about bacteria that are lactic acid producing bacteria, right? Don't you do some tests, like some cultures of things where you test and it, ooh, this turned colors because it produced lactic acid?
Yeah, but we didn't talk about any of the reasons behind anything.
No, I'm not. I don't care about the reasons. I'm just talking about, right? So there are some bacteria that instead of doing ethanolic fermentation, prefer to do lactic acid fermentation under anaerobic conditions. There are lactic acid bacteria. A lot of them are bacilli. There's a lot of lactobacilli. What are things